For our final speaker of the session, I'd like to introduce Professor Scott Barnett. Professor Barnett is at Northwestern University in the Department of Materials Science and Engineering. He is a GCEP PI on the effort entitled A Novel Solid Oxide Flow Battery Using HCO Chemistry. He received his PhD in metallurgy from the University of Illinois at Urbana-Champaign and did postdocs at the University of Illinois as well as Linköping University in Sweden. He has gained a lot of fame and attention for his work on solid oxide fuel cells, among other things, and has published approximately 200 papers in peer-reviewed journals as well as 12 issued patents. So please join me in welcoming Professor Barnett.
Thanks very much. Well, I'd like to start by thanking Sally and all the organizers from GCEP for organizing a really exciting and interesting meeting. Enjoyed it very much. And so today I'd like to talk about the project we have. We've been working on this under GCEP funding for about a year or so with the team that's given here. So myself, Scott Barnett, Gareth Hughes, and Jean Gao at Northwestern, Bob Key and Rob Braun, as well as Chris Wendell and Tejman Kazimpour from Colorado School of Mines. And we had this idea for a new storage technology, and we also, since it's new, we decided to coin a new term, which we called it a solid oxide flow battery. And as we'll see as we go through the talk, this involves a kind of novel storage chemistry for this kind of device. Okay, so this is illustrating in a cartoon fashion what this solid oxide flow battery looks like. It's really based on solid oxide fuel cell, or SOFC technology. Okay. And, but on the other hand, it operates like a flow battery. So you can see here, this is meant to indicate a stack with the electrolyte and the two electrodes on a typical solid oxide fuel cell stack. But instead of bringing in a fuel and having exhaust, it's hooked up to tanks. So you have a feedstock tank, fuel storage tank, and this can be operated either in a fuel cell mode or an electrolysis mode. And what's shown here is actually the electrolysis mode. So you could actually be bringing in energy from a renewable energy source, a wind array or solar array, bringing in a feedstock like steam, ripping the oxygen off and producing hydrogen fuel that you then store for later use. And then when you need the electricity back, you're going to turn this thing around, run it in the opposite direction, and bring the hydrogen back out of the storage tank, oxidize it with oxygen from air, and then, of course, produce steam as the product and put that back into a tank, and you get, as a result, power out of that. Okay. Now, this basic concept has been around for a while, but the really unique aspect of what we're doing here actually is the fact that we're using a different storage chemistry, actually introducing carbon into the mix instead of just hydrogen and oxygen, but still this same kind of reversible device. Okay. Now, flow batteries, as many of you know, have some nice advantages. And in particular, one of the key advantages for large-scale grid storage is the fact that you can scale the size of your stack to provide the amount of power requirement you have to be able to store or supply. And then you can store the size of the tanks to fit to the energy storage. So that means if you want to do this time shifting over 12-hour storage or so, which is a very difficult requirement for batteries, in this kind of device, you don't have to change the size of the stack, but what you can do is to increase the size of these storage tanks. Okay? And the idea is that hopefully those storage tanks are much less expensive than building a larger electrochemical device. Okay? And one distinction between this and a conventional flow battery is the fact that in this case we're filling these tanks with very inexpensive feedstocks. Water and CO2 are the starting materials. Compared with the conventional flow battery, which has a liquid electrochemistry, it's a fairly expensive liquid electrolyte that you have to fill those tanks with. So as you scale the device up to larger and larger energies, longer times, that also increases the cost of the device. Now, as we've heard in the previous talk, and I want to thank Yi for giving a very nice introduction to this whole topic of energy storage, the cost is a very big issue. And I'm actually showing just a different form of one of the plots here that Yi had shown. So this is a plot showing the capital cost per cycle of energy storage for a variety of different devices. And the problem that Yi already outlined was the fact that due to the cycle life, a lot of the devices that we know and love, things like lithium-ion batteries, actually come up with fairly high storage costs when you consider in the total life of the device. But we thought there was some potential here for these solid oxide flow batteries, which are based on an existing solid oxide fuel cell technology. So we can build on a technology that's already well developed. And indeed, there's been enough studies done that people have an idea of what the cost of these things are. So solid oxide fuel cell devices are thought now to be able to be manufactured at less than $800 per kilowatt. If you then use that for storage over, say, a 12-hour time period, that works out to less than $70 per kilowatt hour of storage costs, which is already getting into the range where people want to see that. And then if you work it out, assuming that we can have good enough storage lifetime, say 4,000 cycles or so, good round-trip efficiency of 80%, that works out to less than 2 cents per kilowatt hour, again in the range you want to be as far as the economics. The issue, of course, is that these devices haven't ever been operated in this fashion. Solid oxide fuel cells are normally run just with a constant current, not with constantly switching the current back and forth between electrolysis and fuel cell mode. So we have to be able to figure out if these devices can indeed provide the requirements. And this plot is just showing a number of different devices and the types of cycle lives they have, and also the efficiencies. One of the big issues with fuel cells, and we have a lot of problems at fuel cell conferences trying to convince fuel cell people that we can actually realistically think about making a device that's going to have 80% round-trip efficiency based on a fuel cell. They just shake their heads and say, you're crazy. But we're still trying to convince them. So, and then the other issue, of course, which we're going to talk about later, is the cycle life. Okay, so with that introduction, I want to go through and talk about a few different points. Give the basic background on this argument of efficiency. How do you get a high efficiency out of a fuel cell-based device as an energy storage system? And it turns out that the key of this is the storage chemistry, as I'll describe. Then I'll talk very briefly about how we've set up our GCEP project and our team, and then summarize some of the results we've had in our work so far. Okay. So this is showing a plot that's showing just sort of typical current voltage curves for a couple different kinds of devices. One of them is a solid oxide, basically solid oxide fuel cell. SOC is just short for that solid oxide cell. This is showing the potential of the device as a function of the current flowing through the device in both directions. So here's the zero in current. If you go to the right here, you're in fuel cell mode, and you're dropping below the Nernst potential, drawing current through the cell, and operating at a lower potential. If you go in this direction, then you're operating in electrolysis mode. And you would be putting in energy and producing a fuel in that mode. Okay? And the first one I've shown here is basically a low temperature fuel cell, proton exchange membrane fuel cell. That's the red curve here. And there's actually been a lot of work on energy storage done with these devices, but one of the problems is that because they're operated at relatively low temperatures, even with catalysts like platinum, they have rather large overpotentials. So that means when you start operating this thing in fuel cell mode, by the time you get up to a sort of useful current density, say on the order of ½ amp per square centimeter, you're already down at about 0.7 volts operating voltage. And then when you want to go back and run it in electrolysis mode to store energy, you're way up here at 1.8 volts operating voltage. Okay? And it turns out that if you try to calculate the efficiency for any kind of device like this, basically a battery, the efficiency is just the energy you get out relative to what you originally put in. And that's basically the charge you store during the fuel cell mode versus the fuel cell voltage divided by the electrolysis charge and voltage. If you assume you don't have a leaky system, these charges are the same, and it's basically just the ratio of these voltages. So if you go back to the PEM fuel cell case, 0.7 over 1.8 volt, that's only about 40% round-trip efficiency. So you're already behind the 8-ball with that technology. The blue curve here shows the solid oxide fuel cell because it's a higher operating temperature, around 800 degrees centigrade or so, has lower overpotentials. You can see that there's a smooth curve here with very little overpotential. If you go through the same exercise and figure out the voltage here at 0.5 volts in both modes, you're at about 0.87 divided by 1.07. That gives you about 80%, at least for an ideal efficiency. Okay, so there's some hope there. And I'll talk a little bit later about when we go through a whole system modeling aspect of this that looks like it's even feasible in a real-life case to think about 80% round-trip efficiency. Okay, now with all that said, there's still a problem in all this. So this is a high-temperature device, and when you're doing the electrolysis reaction in these devices, it turns out that the typical electrolysis reactions are highly endothermic. Okay, so if we take this one just splitting water to hydrogen and oxygen, if you look at the delta H for the reaction, it's highly endothermic. And what that means is that when you're operating the device, the electrical energy you're putting in during electrolysis has to at least match the thermal energy required for the reaction. Okay? And that equality is actually given by this expression here. So the delta H for the reaction is basically proportional to the voltage that you're operating the device at. And Z and F here are just constants, so the Faraday constant and the charge on the ion in the device. And so this voltage here represents what we call thermal neutral voltage. So you're putting in enough electrical energy to compensate for the thermal energy requirement of the device, or of the chemical reaction. Okay? And so the electrolysis voltage then should be higher than thermal neutral voltage given by this. For steam electrolysis with this reaction enthalpy, turns out you need to be above 1.3 volts. If you're doing CO2 electrolysis, you actually need to be above about 1.5 volts. Unfortunately, now if we go back to the efficiency calculations we had before, I was actually talking about operating at about 1.1 volt in electrolysis mode. Now we're seeing in reality with these reactions, you need to operate at a higher voltage, like 1.3 volts, and now your efficiency is much lower if you do the CO2 reaction, even lower, like 60%. Okay? So that's really where our key innovation comes in here. Okay? So that's for simple energy storage chemistry. So we had an idea for an alternative chemistry where we actually combine both CO2 and steam electrolysis at the same time. So to understand this, I'm going to just introduce quickly this composition map. So to show how we're doing this, here's a map showing carbon, hydrogen, and oxygen and various combinations of compositions of these things. And just to give you a reference point on the bottom, this blue arrow here shows here typical steam electrolysis, where you're going from hydrogen-rich to steam-rich and back and forth again. What we're doing now is to add some carbon into the mix and going up, for example, to this point on the curve. Again, this line is basically going through the oxygen apex here, so you are basically keeping the same carbon-hydrogen ratio, but putting oxygen in or taking oxygen out as you do electrolysis or fuel cell operation. Okay? It turns out there's limits to where you can work, and it's basically in this region here, because this line represents fully oxidized steam and CO2, so you obviously can't go in here. And it turns out that if you become too carbon-rich, it becomes unstable to actually forming solid carbon, and you muck up your device with carbon, and you look very silly. So here's a little bit more focus on what we actually ended up coming up with as a model system for our storage chemistry. So this is just focusing in on this 1/4 of the diagram. Here's the carbon-hydrogen ratio that we chose. And so we're basically coming up with a storage system where we have one of the tanks here, which has the oxidant-rich gas, which we call 0.1 in this tank. We're putting it through this thing, running it as a fuel cell, and then putting the resulting gas and storing it, running it as an electrolyzer, producing a fuel, which is coming out at this composition here. Then we turn it around, run it as a fuel cell, oxidize the gas, and move back to this point here and produce the gas that goes in this tank. Okay? And the key thing is, though, what are the products of that reaction? And what the key is, actually, as it turns out, is the product of electrolysis. Okay? So if we do that with a mixture of steam and CO2, and we do it at a typical SOFC operating temperature, which is about 800 degrees centigrade, and we do just equilibrium thermodynamics, we see that the products are mainly hydrogen and carbon monoxide. So what we've done is just we've taken steam and CO2 and electrolyzed them to hydrogen and CO. So nothing special, and that doesn't do us any good, but it turns out that if you actually drop the operating temperature, say to 600 degrees centigrade or so, you actually start getting some different products. In particular, you can see you're starting to produce a substantial amount of methane in the product mix. Okay? And by the way, I just want to illustrate these data points show that these are actually measured compositions, so showing that the thermodynamic compositions are actually reached in practice in these kinds of devices. Okay? And so based on this, based on knowing what these compositions are, we can go back, calculate new delta H's for the reactions. Okay, so these are now different because we have different products. And it turns out that if we do that, we see that the thermal neutral voltage at the high operating temperature, again, is fairly high, 1.3 volts. But if we drop the temperature down to, say, 600 degrees centigrade, where we're starting to get these other products, we see that this thermal neutral voltage is dropping down to around 1.1 volts. Right into this range here, the gray area is here is where the Nernst potential for the cell is. So that means we've eliminated this limitation of needing to have the electrolysis voltage as a very high voltage to maintain the cell operating temperature. Okay? And that was going to allow us to get a high efficiency in this process. And this plot is just showing that you can obtain a similar result not by lowering the operating temperature of the cell, but by pressurizing the cell. Okay? So this is showing this thermal neutral potential as a function of operating pressure of the device, you can see even at a typical operating temperature of something like 750 or 800 degrees centigrade, once you get up to 10 atmospheres or so, you already have a fairly low thermal neutral voltage. Okay, so this gives us actually a couple of operating modes that we can operate this device in, and based on these considerations, we came up with some requirements on these devices. Okay, so first off, we need to have a device that's going to give us a very low polarization resistance in order to allow us to operate under these conditions. So basically what I just said was that we want to have a high efficiency like 80%. For example, we might want to operate in fuel cell mode at 0.9 volts and electrolysis mode at 1.1 volts with a 1 volt Nernst potential. Okay, so that means that the overpotential of the device that's operating at 0.1 volts, if we want to get a reasonable current density like half an amp per square centimeter, that means the resistance of the device has to be 0.1 divided by 0.5 or by 0.2 ohm cm squared for the resistance. And this is, if you look at fuel cell literature, this is actually a fairly challenging number, but not totally out of reach by any means. And we have the two options for doing this. One is more normal SOFC operating temperatures, but pressurizing. Okay? And this is a range actually where we think fairly conventional SOFC stacks are very close to meeting this requirement. And the other one is a lower operating temperature device that could operate more like atmospheric temperature. But here we need some alternative materials, non-conventional materials. For example, a typical SOFC has a zirconia electrolyte. That doesn't have a high enough conductivity at 600 degrees centigrade, so we're starting to use some alternative higher conductivity materials. Okay, so that's the background on our idea, and now I just want to outline what the GCEP project is about. Okay, so the questions we're trying to answer are, can we make solid oxide fuel cells or solid oxide cells that can meet the requirements we've been talking about? That means this low cell resistance, and also can they work without degradation over many years and many thousands of charge-discharge cycles? Okay. Second of all, can we really achieve this kind of round-trip efficiency that we've been talking about on a kind of ideal theoretical basis, but actually in a full system? Okay. And based on that system considerations, what is the best way to do this? The high temperature or the low temperature case or the high pressure case? What are the best overall system designs to make this work? And can we really provide cost-effective energy storage on a grid scale? Okay. And as I already mentioned, our team here, in our group at Northwestern, we do mostly cell materials and fabrication and testing, so we're providing that part of the effort. Bob Key does a lot of very nice work on cell and stack level modeling, and Rob Braun does system modeling, so we can cover the whole gambit of the device here without actually having to go about the huge expense of actually making full operating devices. Okay, and to do that, we're using a concurrent R&D approach. So that means that on our side, for example, we're making materials and testing them, providing them input that can be put into the models to get more realistic stack and system simulations. And on the system side, they're providing us key input as far as what we need the devices to do and what kind of conditions we should test them under. I should point out this work is going on over multiple length scales. This is just kind of a cartoon illustration showing an example of a tubular solid oxide fuel cell, just trying to illustrate the fact that to understand how these things work, we work over many length scales, both on the modeling side and the experimental side. So you've got on the atomic scale, heterogeneous reforming reactions, electrochemical charge transfer. On the particle scale, so if you look inside these electrodes, they have sort of micron scale particles where all of the electrochemistry is going on. The scale of the electrodes is sort of up to millimeter scale, and finally up to the cell or stack or system level, so millimeter to meter. Okay, so I wanted to go over some of the results and just highlight some of the things we've been doing so far in the project. Okay, as I mentioned, one of the ways to do this is by making a cell that works at a reduced temperature, so we've been working specifically on that. So just some brief results on that. As I mentioned, one of the key problems with making a lower temperature cell is to get away from yttrium-stabilized zirconia electrolyte. So we've been looking at this newer electrolyte material. It's a lanthanum gallate, or LSGM for short, which has a higher conductivity at low temperatures. But one of the problems with this material is that it's traditionally had processing problems, and one of the common electrode materials contains nickel, for example. Well, that reacts strongly with LSGM. So that's a problem. Another one is to get these things to work at low temperatures, you really need highly active nano-electrode particles. Okay? So we came up with a scheme for making these things in which we actually start out with a structure that looks like this. It's all LSGM. We can take this and fire it at very, very high temperatures, 1400 degrees centigrade, to produce this structure. And then later on, we can introduce in some of these materials at lower temperatures and avoid some of the reactions. Okay? So for example, then we infiltrate in a nanoscale cathode material. We're using, for example, samarium doped strontium cobalt oxide is a very active oxygen reduction catalyst. On the other side, the fuel side, we're infiltrating nanoscale nickel onto the support, which provides also highly active structure. This is just kind of a low magnification view of what the structure looks like, so you can see the porous structures of either electrode and a thin, dense electrolyte structure. Since you can't see this too well, I want to zoom in. And this shows, zooming into this anode structure here, you can see within the pores here, and you can actually see now a little bit of this nanoscale nickel structure on those, which provides highly active reactions. And this is an even higher magnification view, showing some of these particles are down to the sort of tens of nanometer scale. And it turns out that some of these devices have actually produced what we think are some of the best reported power densities as fuel cells that have ever been reported for devices operating less than 600 degrees centigrade. And this is just showing one of the results that we published recently on this, showing getting power densities well in excess of 1 watt per square centimeter at 600, or well below 600 degrees centigrade, which is a pretty remarkable result. Second point I wanted to talk about is work we've been doing on cell durability. So this is the question of how many cycles can we go through on this device. Okay? And one of the problems we have is that solid oxide fuel cells have not really been operated in this mode. So we don't know how they're going to operate with cycling. So that's one of the first things we're really looking at. Here's an illustration of some data, and I realize this is a little bit small. This is showing basically the resistance of the cell as a function of time. And this is an experiment where every half hour we switch the current. So a half an hour we run the current, in this case at 0.5 amp per square centimeter in electrolysis mode. We turn it around and then do fuel cell mode for half an hour. So every hour basically we're cycling this thing. So this test you can see was over about 350 hours. So we're at about 350 cycles of this device. Of course, we want to get up much more, like 4,000 or 5,000 cycles, but this is just kind of the beginning. But the good news here, without getting into the details, the red and the green here are just showing different parts of the device. The blue is the overall resistance. You can see the device is actually pretty stable. It's actually improving slightly over these first few hundred hours of operation. Okay. Not so good news if we try to go to much higher current density. So if we want to run these things at much higher powers, this is now 1.5 amps per square centimeter, and we are seeing degradation. This is actually maybe an opportunity where we can actually use the higher currents to kind of accelerate degradation and study what are the processes going on. And we are planning very detailed studies of this. And one of the tools we're using is three-dimensional imaging of the electrode microstructure. And this is actually showing some examples of a typical electrode structure, which is actually a fairly complex multi-phase structure. And this is just illustrating some different ways we can view that structure. We can look at particles, how they're connected within the structure. Those green lines there you're seeing are actually three-phase boundaries, which are the active sites for electrochemistry in these cells, electrodes. And we're using a variety of techniques for characterizing these. So what we want to do is to be able to go in before and after cycling these devices, after degradation has occurred, go in and look at the microstructure and try to understand what are the mechanisms of degradation so we can hopefully avoid them. Another thing we can do is we can take this structure, port it into an electrochemical model, and this is actually a result from Bob's group where we've done that. We've taken a three-dimensional structure, put it in, and he started calculating the transport of electrons or ions or gas phase through the different phases that are present in the electrodes. And finally, a very important aspect of this work is system design. And so the other group at Colorado School of Mines, Rob Braun, is working on the system level modeling. And this is just to show you that we actually are now putting this thing in not just a very simple model, but a realistic model. We now have our reversible solid oxide flow battery stack here. We've got the storage tanks that we were talking about, but now in addition we have all of the other components that you would have in a real device. So we have heat exchangers here, we have compressors, and this is showing, for example, in fuel cell mode that you would be bringing fuel in from the fuel storage tank through a heat exchanger into the cell, exhaust comes out, the hot exhaust comes out, heat exchanger again, which heats up the incoming gases here, finally into a compressor and then into a storage tank. reverse direction electrolysis mode, using the same components, but now things are flowing in the opposite direction as you're doing energy storage. Okay, so now we can run through complete modeling of an entire system, and we're beginning to get results on this that look very promising. And this is just illustrating that some of the results of that showing efficiency, in this case as a function of this resistance of the cell that I've been talking about. Okay, and this is showing, actually breaking it down into the electrolysis mode and the fuel cell mode efficiencies, and this is the overall round trip efficiency. Okay? And what we can see here is that if we get down to this value of about 0.2 ohm cm squared that we were talking about, actually in a realistic system, and these different curves here are showing different assumptions, which I don't have time to get into, but basically we are getting, in a real system with all the losses in it, compressors and heat exchangers and whatnot, we can still contemplate the idea of getting 80% round trip efficiency on these devices. Okay? And I put this in here, Rob, so I wouldn't forget to mention this. One of the students from Colorado has got a poster that is still up because it won an honorary mention. So you can take a look if you want to see more details on the system modeling. Okay? And that's the end of my talk. I just wanted to reiterate what I had talked about. So we've introduced this solid oxide flow battery, which we think has some significant advantages for large-scale electrical energy grid storage. The key point is that we use a less endothermic methane-based storage chemistry using either pressurization or low temperature operation in order to get high round-trip storage efficiencies. And in our GCEP project, we're looking at low temperature cells, pressurized testing, durability, cell and stack level modeling, and finally system design and thermal management. And that's my talk. Thank you very much for listening.
It would seem to me that one of the problems with using gas as a storage, something to store, is that large volume, and you need to pressurize it to keep the storage volume smaller, the container small. Did your energy efficiency include pressurization costs in its efficiency?
Yes, it did, and that actually is a very important consideration. I don't know if, Rob, you want to weigh in on this, but it turns out that the pressurized mode of operation turns out to be pretty advantageous for this because of the fact that then the pressure ratio between the device and the storage tanks is much less. And that reduces that parasitic loss of compressing the gases very significantly. So that result I showed, the very last result, was done under pressurized case, I think 20 atmospheres. And that's a very significant savings by doing that. What was the storage? So the storage pressure was 25 and the stack temperature was 20 atmospheres now.
So you gave an example of half-hour switching back and forth from charging to burning. So are there limits on that? I mean, you can imagine some fluctuations on the grid, for example, that with wind turbines, they can be even down in the millisecond time range. So we talk about the range of reasonable operation from switching back and forth.
Yeah, that's an interesting point. So I didn't show the result in here, but we have looked at how fast the device switches. And for a small device, it's extremely fast. So basically going from 1.5 amps in one direction, 1.5 amps in the other direction, our shortest measurement time was 2 seconds. And the device had already gotten to within about 20 millivolts of its final voltage very rapidly. So that intrinsically the device is very fast. So you could contemplate this not just for long term, but potentially some load leveling. But I should say as a caveat, once you make this into a much larger stack, then you've got a lot of chemical mass and thermal mass that would need to be shifted. That's a different question, but maybe one that we'll get into later on in this project.
I have a question I'd like to ask as well. The question is, since you've designed this system, which is, I think, a great way, the right engineering approach with big, large-scale systems, my question is, have you done any techno-economic analysis based on the storage tanks, the compressors, the pumps, and this to get at least a baseline cost of what the balance of plant would be, which could then help tell you really how expensive the SO flow battery would be or needs to be?
Yeah, that's a very good question. We haven't gotten too far into that. Certainly the tanks is, we haven't looked at it all. To a large extent, some of the numbers that I presented very early on in the talk, so the $800 per kilowatt for a solid oxide fuel cell, that was for a system. Okay, so that's including all of the balance of plant, but not tanks. And so that's an estimate, but it was kind of handed down from on high by Department of Energy, so we believe it, and we like the number. So.